Today, we're discussing a very famous series called Harmonic series. Most people think, and your math teacher most likely told you that harmonic series diverges. This is a joke. In fact, it converges. Let's look at the series. As n increases, every term grows smaller. Intuition tells us that series converges to a finite value. There are so many examples. We can easily conclude that series whose term grows smaller eventually converge. Therefore, we reasonably conclude that the harmonic series converges. Another way to approach this is look at the function 1 over x. By drawing infinitely many rectangles with width 1 under the graph, we find that the sum of their areas 1 plus 1 over 2 plus 1 over 3, etc. is equal to the sum of the harmonic series. Now observe this shape. It is the area bounded by 1 over x, y equals to 0 and y equals to 1. With some piece of cake integration, we conclude that this area is infinite. We find the rectangles are always contained with this shape. Thus, the sum of the rectangles is less than infinity. Thus, the harmonic series converges to a smaller than infinity, or say finite value. You must have tried stacking coins, like this. Stack one coin on the top of the other, and try to make the stack as wide as possible without toppling over. Have you ever thought about how wide the stack can possibly be? We use a rectangle with length 2 to denote a coin with radius of 1. For those who have studied physics, you will know that the key condition to the stack not toppling over is that the center of gravity of the upper coins does not exceed the lower coin's surface of support. If it does, the upper coin will topple over. How so? Let's start from the uppermost coin. In order for the first coin not to topple over, its center of gravity can only be farthest on the edge of the second coin. Thus, the uppermost coin extends the width of the stack at most by 1. We apply this argument to the combination of first and second coins. Their combined center of gravity must not exceed the edge of the third coin. Thus, the second coin extends the width of the stack by at most 1 over 2. In the same way, the third coin could extend the width at most by 1 over 3. We can generalize the observation by the lever rule to any nth coin to conclude that the nth coin extends the width of the stack at most by 1 over n. You may pause the video here to do some calculation yourself to be sure. Thus, the maximum possible width of the stack is the sum of the harmonic series 1 plus 1 over 2 plus 1 over 3, etc. What does this imply about the claim that the harmonic series diverges? This means that if a harmonic series diverges, given enough coins, we can make the stack infinitely wide. It doesn't take a physics teacher to tell you how ridiculous it is. Therefore, the harmonic series must converge. You might say, this is too complicated. Is there a more rigorous and elegant mathematical way? Okay, we want the sum of reciprocals of all positive integers. Here's a small trick. We split all positive integers into two types, those that contain the digit 9, such as 9, 19, 29, and 97, and those that do not, such as 1, 2, 3, 4, and 18. So, we split the sum into two parts. First, let's look at those without 9. For one digit, we conveniently add them up and obtain a value that is approximately 2.718. We simply consider that the sum is less than 3. Now, let's move on to two-digit positive integers without 9 and classify them into 8 rows according to their tenths. Pay attention to the fact that every single reciprocal is less than 1/10, so the sum of reciprocals for the first row is less than 9 times 1/10. For the second row, the value is less than 9 times 1/20. We can obtain a similar upper bound for every single row. When we sum these bounds, we conclude that for two-digit positive integers without 9, sum of their reciprocals is less than 3 times 9/10. Similarly, we can group three-digit positive integers without 9 by the first two digits. Here are some examples. We find that the sum of their reciprocals is less than 9/10 of the value that we just calculated. Therefore, for 3-digit numbers, the sum of their reciprocals is less than 9/10 squared times 3. Let's take a step back and look at what we have found so far. For all positive integers without 9, the sum we are interested in is the sum of sums for all positive number of digits. After grouping the factors, we are looking at a geometric series. According to formula, the sum of the series is 30. This is the upper bound of the sum of reciprocals for positive integers that do not contain 9. Now, let's shift our attention to the other group. For 1 digit, there's the only line. Apparently, 1/9 is less than the sum of previous 8 reciprocals because 1/9 is smaller than any of these terms. Same for 2-digit numbers. There are not only less values containing 9, but they are also on the very edges of our list. In fact, we can conclude that, on a grand scale, the number of integers containing 9 is negligible compared to those that don't. Therefore, the sum of their reciprocals is also reasonably bounded. Let us be rigorous here. For integers that contain 9, sum of reciprocal is less than 30. This sum is at least greater than that for integers who do not contain 9. Therefore, the harmonic series converges to a value that is no greater than 60. Mathematicians don't know much about the magical value, but using a not-so-certain calculator, we evaluate the sum to be uncertainly 41.9999999999999999999999999999999999999999999999999999999. Oh, I should remember you that this is a rough approximation, but the uncertainty should be no greater than 6.626 times 10 to the power of 34. Great! This is the end of this video. The next one on schedule, if we have chance, will tell you why the Earth is flat. If you like this video, upvote and like it. Thank you for watching.